video we'll give examples on the formal definition of a limit. Find and prove the limit as x approaches 4 of the function 2. So obviously this limit is just equal to the value 2, and now we just have to prove it. So remember that our formal definition of the limit said that for any epsilon greater than 0, there exists a delta such that f of x minus the limit, which in this case is 2, is less than epsilon when the distance from x to the value that it's approaching is between 0 and delta. Now what we can do here is plug in our value for f of x, and so that just becomes the absolute value of 2 minus 2 less than epsilon, or 0 is less than epsilon. So this means that for any epsilon that's greater than 0, this holds true. So we can choose any delta we want, and our definition of the limit will still be satisfied. Here's another example that's a bit more complicated. So first, we'll just start by finding the limit. So we can just plug in 3 into our function, and we end up with the value 10. Now again, we'll look at our definition of the limit. So for any epsilon greater than 0, there is delta such that the absolute value of f of x, so I'm just going to go ahead and plug in f of x, 2x plus 4 minus the value of our limit, which we found was 10, is less than epsilon when absolute value of x minus the value that it's approaching, I'm going to go ahead and plug that in as well, is between 0 and delta. We can do some algebra on this expression over here. So we'll have absolute value of 2x minus 6 is less than epsilon. We can take the 2 out of the absolute value. So the absolute value of x minus 3 is less than epsilon over 2. And obviously absolute values are always greater than 0, so we can just go ahead and stick this in. And now look, we have an expression that looks very close to what we wanted, which means all we have to say is delta equals epsilon over 2, and our definition for the limit holds true. In this case, we're going to look at a case where someone incorrectly gave an answer for the limit, and we're going to use the formal definition to prove why it's incorrect. So we have our function defined as this. We can just graph that to better understand it real quick. It's going to equal -1 for x less than 0, and then 1 for x greater than or equal to 0. And here we're saying that the limit as x approaches 0 equals 0. But obviously this is not true. We know that in fact the limit does not exist. But how can we prove that this limit is incorrect? All we have to do is find one epsilon for which there is no delta that satisfies our definition of the limit. Now let's look in more detail at this expression right here. we've said that f of x is equal to either -1 or 1. So, in the first case, if f of x equals -1, then we end up with the absolute value of -1 minus 0, which equals 1. In the second case, where f of x equals 1, then we have the absolute value of 1 minus 0, which again equals 1. So no matter what, this expression always equals 1, and so we're saying that 1 is less than epsilon. So now, what if I choose an epsilon that is less than 1? Let's say I want epsilon to equal 0.5. In that case, we end up with the statement 1 is less than 0.5, which is never true no matter what delta we choose. Therefore, our limit must be wrong.